Let's start today with some review from last time. And actually, even before we get into the review from last time, I want to take a look at this tweet that came up yesterday from Chris Olah about linear algebra and machine learning. And my goal here is to bring out the idea that this linear algebra stuff we've been developing, it's not just because I have a math background and I think it's pretty. It's also very deeply connected to machine learning and understanding the structure of data sets. And this guy, Chris Olah, is a very well-known deep learning researcher at Google. He's done a lot of really cool stuff to make deep learning accessible and captivating. So distill.pub, the website, is something he's been involved in from the beginning. And he's done some other cool stuff, made some really cool blog posts. So anyway, he's talking here, I'll let you read it, but he's talking here about how linear algebra is more interesting when you have examples to draw on. Specifically, he's talking here about machine learning examples. And he goes on to sort of share some candor about the details of his expertise, what he understands really well, and how that helps him effectively understand problems. And specifically, he mentions the singular value decomposition, which is what we've been building towards with the stuff that we've developed in the linear algebra part of the course, and something called non-negative matrix factorization, which is also something that we've talked about, although indirectly and only part of it. It has to do with this idea of dimension bottleneck. So if you realize a map as a composition of two maps that go sort of down to a much lower dimensional space and then back up again. So we talked about that idea, we called it a bottleneck. So that's what non-negative matrix factorization is related to. So anyway, I just thought this came up yesterday. I thought it was an interesting thing to point out. But let's go ahead and get into the review questions from last time. So we're going to just do a handful of review questions from the linear algebra stuff, and then we'll move on into today's topic, which is calculus. So here's my first question for you. How do you project onto a unit vector? So in other words, if v is a unit vector and u is some other vector, how can we calculate the component of u in the v direction? So that's this orange vector here. How do we come up with its magnitude in a simple way? Okay, cool. I'll share a few answers here. Great. So Yoon Kyung, would you like to talk about your answer? Yep, great. Yeah. That's right. So u dotted with v is going to give us the magnitude or length of this orange arrow here. And so if we want the actual orange arrow, we need to multiply that by the direction, which is the unit vector v. So sort of a couple different perspectives there. We can either talk about just the dot product with u and v, or we can talk about the dot product of u and v times v. So we have those two different answers, and they both make sense. It's just a question of whether you want the actual vector or just the magnitude of the vector. And if you recall, the reason that this formula works is that what we want to have is v dotted with u minus this vector that we're looking for, the orange one, equaling 0. So in other words, we want this vector u perp, which is the difference between u and u parallel, we want it to be perpendicular to v. So we can write that down as an equation, a dot product equation. And we want to say that u parallel has to be in the direction of v. So we call it k times v for some unknown value of k, and then we can just solve for k, and we just get u dotted with v. So just distribute the dot product here, rearrange a bit, and we just get the dot product coming out. So this is something you can really hold on to. Aside from all the formulas, to project onto a unit vector, just dot with that unit vector. That's it. That's the punchline for computing projections. To project onto a unit vector, just dot with it. Okay, so here's another question. This is the second most important idea to take away from the orthogonality discussion. How do you find the component of u, which is orthogonal to a vector space? So for simplicity, assume that the vector space is specified as the span of a list of orthonormal vectors, meaning that they're pairwise orthogonal and each has a unit magnitude. So what can you do with u and these v vectors in order to come up with the component of u, which is orthogonal to the space spanned by the v's? All right, cool. So several correct answers here. That's great. Yeah, so Yash, do you want to talk about the motivation for this formula here? Yeah, that's great. That's perfect. So this is the picture you want to have in mind. You've got these two vectors, red and gold, and they're already orthogonal and normalized to have unit magnitude. And then you have this other green vector or sort of teal vector that comes along, and it's not perpendicular to the first two, and you want to sort of make it perpendicular. And the idea is you're just going to calculate the component in the red direction and subtract that off. You're going to calculate the component in the gold direction and subtract that off. So you'll have two vector subtractions here. And that will eliminate the sort of part of this teal vector, which is leaning in the same direction as the plane. And you'll just be left with this blue part that points orthogonal to the plane. And that works in general. So if you want a formula version of this, here's what it looks like. So the part of u that's perpendicular to the vector space is u minus its projection onto each of the vectors. So we dot with each vector and then multiply by that vector, because we do need the actual vector here, not just the length. And then we just repeat. We keep subtracting off the components in each of the existing directions. And that's going to give us the component of u that's perpendicular to the vector space. So we can do this more conveniently using matrix multiplication. And it's really pretty helpful to get to the place where we've encapsulated all of this logic into a matrix operation. So how can we build a matrix V with the property that multiplying V transpose by a vector U projects U onto the span of V1 up to Vn and gives us the components of that projection? So in other words, we just want to compute in this picture the projection onto the red vector, the projection onto the gold vector, and collect those components. How much red do you need? How much gold do you need? Into a vector with just, in this case, two entries. So how can we build a matrix that has this property? So we talked about this last time without the transpose, but that's not too big of a deal. We'll see in a second why we're doing that. So what's the idea? Great. So a few folks are still working on their answer and look like they're on the right track, but let's go ahead and share Yasha's answer here and then move on. So what we want to do is define V to be the matrix whose columns are given by those basis vectors V1 up to Vn. That's exactly right. So let's take a look at why that's the case. So the values that we want to compute are the dot products of the V's with the U's. So that's what we've been saying. If you want to project onto a unit vector, just dot with that unit vector. So we want V transpose to have the property that the V's are its rows. That way, when we compute the matrix product, we're going to be dotting the rows of V transpose, in other words, the little V's, with the vector U that we're multiplying by. So in other words, the little V's should be the columns of this matrix big V. And again, that's because you can think of multiplying a matrix by a vector as dotting the rows of the matrix with the vector. So that's just a different perspective on matrix multiplication. Okay, so let's take that one more step. So if we let V transpose be this matrix we just said, this right here should say rows. So V itself is the matrix whose columns are V1 up to Vn. Then if we want to throw the little V's back in there so that we have an actual vector instead of just the components with respect to V1 up to Vn, what we can do is just multiply by V here on the left. And that tells us that VV transpose is the matrix that maps U to U parallel. So the projection of U onto this vector space. And the question I have now as a follow-up question to that is, what's the matrix that maps U to U perp? So we know how to get U parallel, the part that's in the vector space, when we project down onto the vector space. What about the other part, the perpendicular part? How can we come up with a matrix which takes us from U to U perp? And here's the corrected version. So yeah, so for some reason I had minus signs in there. Of course, it should be plus signs. And then also I had this transpose messed up in the top. So that's fixed. So anyway, that'll be slightly out of order if you answered. Sorry about that. Yeah, so we had a couple correct answers here. Let's walk through this. So this one was, I guess, pretty tricky. It's helpful to see, though, as a way of reinforcing the ideas we're learning now, and also it's an example for when this pattern comes up in other contexts. So the main idea, as we've been discussing, is that to get the perpendicular part, you subtract off the parallel part. So once you have the projection onto the vector space, you just subtract that off from the original vector, and that gives you the perpendicular part. So since we have this formula for the projection, we can say u minus VV transpose u. That's going to be the perpendicular part. But then what we can do is we can write u as the identity matrix times u, and that allows us to sort of factor out the u, as it were. So we can, once we write this as identity matrix times u, we can use the distributive property to pull this out. And that's telling us that the matrix that we're looking for, which computes the perpendicular component, is I minus VV transpose. And the reason that I threw the transpose in earlier is to make this formula look like the way it's normally printed when people talk about these things. So VV transpose is the projection matrix. I minus VV transpose is the matrix which computes the orthogonal component. And incidentally, you never want to do Gram-Schmidt by hand. You want to get it done in some software. And of course, NumPy has your back for that. So the linalg module in NumPy has a function called QR, and it performs the Gram-Schmidt procedure for you. Essentially, there is one little wrinkle, which is that sometimes there's an extra factor of -1 that gets thrown in. But whatever, that's not a big deal. You're still representing the same reference frame. You just kind of flipped one of the axes around in the opposite direction. So this is essentially the right idea. And this is called, in matrix algebra terms, the QR factorization. So instead of subtracting off all these components, instead what one does is keep up with the Gram-Schmidt procedure in the columns of this matrix Q, which is a standard name for it. And then you keep up with the operations that you performed to get the original matrix into this form Q with another matrix that's called R. And it turns out that, just because of the way the procedure works, its entries are all 0 below the main diagonal. So every entry whose I and j, whose row index and whose column index have the property that I is greater than j, all those are going to be 0. And you're only going to get non-zero entries sort of in the upper right part of the matrix. So it's called upper triangular. Whatever, that's kind of beside the point. The matrix Q is the important one because its columns are the result of applying Gram-Schmidt to the original matrix. So if you want to get Gram-Schmidt to happen, you do the QR factorization in NumPy and then discard the R, just use the Q. And that's going to be your Gram-Schmidt. So we saw this matrix last time, 2, 0, -1, 2, 0, 3. And I'm showing you a different way here of entering a matrix in NumPy, which involves fewer brackets, so it's just less typing. You just enter a flat list and then reshape it according to how many rows and columns it should have. And so you typeset it like this, it still looks fine, but you just, it's just less strokes of the bracket character. All right, so this will be launching my Python session, but the point here is going to be that the matrix Q is the Gram-Schmidt result, or the result of applying Gram-Schmidt to the columns of the original matrix, the matrix that I'm calling A here. So here's a question while that runs. How can we quickly check that a particular matrix does indeed have orthonormal columns? So after we do Gram-Schmidt, it should be normalized in each column, and they should all dot with each other to give 0. So we could write out a bunch of code to check that, but there's a slick matrix way to do it in very little code. How can we check if a matrix has orthonormal columns? Here's the trick. Here's the idea. What we want to do is get the columns of Q to dot with one another somehow. And there's an operation which does this for us. It's transposing the matrix and then multiplying it by itself. And the transpose is going to turn the columns of Q into rows of Q, and then the matrix product here is going to compute dot products of these rows with columns of this matrix. And that's exactly going to be computing dot products of columns with themselves. So that's perfect. And the thing is, like, off diagonal, whenever you're dotting two different vectors, they should give you a dot product of 0. And on the diagonal, you should get a dot product of 1. So let's move on to the main topic for today, which is calculus. And I include this because it is a prerequisite. It does come up in the program in some important ways, and we definitely need to develop these ideas. On the other hand, calculus is something folks often take in high school. There's more consistent coverage of calculus in college. So it's not as important, I think, as the other ones. Also, I polled everyone at the beginning, and folks consistently expressed more confidence in the calculus topics than any of the other topics that we talked about. So that's reflected in the schedule. All right, so let's get into this conversation about calculus and specifically about derivatives. So I'm going to start right off with a question, which is, what mental handles do you have on the idea of differentiation? Like, what are some summary phrases or pictures you have in mind when you think about derivatives? And this is really kind of a word association idea rather than a rigorous math question. So as suspected, the most common one here is slope of the tangent line. So let me share these answers so you can see the ideas people have here. So slope of the function at a point, slope of a tangent line, a couple rate of change in here. So that's good. That's a little bit different. Same idea, slope, but maybe a little more general. Idea of a difference quotient, or we have a tangent plane here. So this is someone who's thinking in higher dimensions already, as opposed to just functions of a single variable. The idea that you're looking sort of somehow instantaneously at a point rather than over some finite stretch. We'll talk about that a little bit. So yes, that's very good. And as I said, the most popular answer here is slope of the tangent line. So this is the picture from the data gymnasia course where the derivative or slope of the tangent line is being recorded by this orange curve. And as we move the point that we're looking at, we get kind of different slope values. So here the slope is 0, here the slope is steeper. You get the idea. And so, this is something you can appeal to geometrically. You could, for example, give a student, as soon as they learn the idea of slope, you could give them this picture of this teal curve and say, okay, draw a curve that only touches this, draw a straight line that only touches this curve at a single point, sort of, kissing it, if you will, and like estimate the slope. So this is a very primitive concept, right? You don't need to get into the idea of infinitesimals to appeal to this picture, and you can stick in your head really well. So this is a perfectly reasonable way to go about it. However, I want to add another mental image to your arsenal here, aside from just this one, which is that the derivative of a function at a point is the scale factor that tells you how to convert from small changes in input to small changes in output. So that might seem like a pretty basic refactoring of the slope concept, but there are situations where it's going to be clearer to think in these terms rather than think about the slope, because there are going to be contexts where the picture is not immediate, and sort of lifting the scenario up into a picture or something where you have a graph is not going to be as easy as just directly reasoning. Here's an example of this in sort of a only slightly contrived real world context. So suppose that R represents your company's revenue as a function of ad spending, which we'll call S. So suppose that given what your ad spending is right now, increasing spending by $1 additional is, according to the research that you do, going to lead to a $3 increase in revenue. So in that case, approximate the derivative of the revenue function with respect to the current spending level. Or sorry, the derivative of the revenue with respect to spending at the current spending level. So that's what this notation is supposed to mean. All right, so folks are on the same page with this one. All right, so that's not too tricky. I mean, there's only one number, so it sort of has to be that number, but also I think, it's pretty clear that this concept is reasonably accessible. So yeah, so from this like scale factor conversion point of view, what you're saying is I put an extra dollar in, how many dollars am I going to get out? And the problem stipulates that answer is 3. It's not so helpful to draw a revenue versus spending graph here. You can already get, from just your experience as a person, you can think about putting $1 on the table and getting $3 back. This is sort of a more basic idea here. We are in this picture, and we'll go into a bit of a diversion about this, we're relying on an understanding that $1 is a small enough amount of money to be small for purposes of thinking about derivatives. So when you take a sort of a big step, what if we spend an extra $1 million on advertising? It's not clear the derivative is going to give you useful information there. The step needs to be somehow small, and that's sort of an imprecise concept. So mathematically, the way we resolve this is by defining a derivative as a limit as the change in input size goes to 0. So anything that happens over any particular finite time scale or scale for the change in input doesn't matter. You can always go smaller and just focus on that, and that is always going to give you all the information that you need to compute the derivative. But this doesn't make sense for functions in the real world. Like, what is the change in revenue if we spend an extra 1 over a Google dollars? If you're asking that question, then already you're taking your mathematical model way too seriously. You can't spend less than a penny, really, and it just doesn't mean anything below a certain scale. So we're going to have this problem often because it's almost always possible for a real world function to zoom in so far that the granularity doesn't make sense anymore. So in practice, the reason we don't end up having to dedicate a lot of attention to this is that we tend to model phenomena with functions whose behavior on smaller scales isn't different than its behavior on the scales that are sort of materially small, things like $1 or $2 of ad spending, versus if you looked at a microcent or something, the function that you're using would behave similarly on those scales. And so you can kind of ignore this issue, but realistically, there are some situations where you might have to keep it in mind. There's always going to be a little bit of a trade-off between taking steps that are small enough for the mathematical derivative to be a sensible concept, but are big enough to actually have some meaning. Okay, so anyway, let's go back to the revenue question. So given this information that r prime equals 3, are you going to recommend, yes, we should purchase an additional $1 worth of advertising? So that's really a yes or no question. There should be suggestion chips. All right, so people are unanimous on this one too. What folks have to say? Yes, absolutely. This is certainly a reasonable take. It is a little bit of a trick question though, because revenue is not really the right thing. So this is not a math point here. This is more of a, I don't know, econ or finance or something. But you might be selling something that costs you $2 to produce. You're making some socks or something like that, and it costs you money to get the material to make the socks with. So it could be the case that $3 of revenue actually loses you money if it costs you $2 or more than $2 to produce the good. So really, we'd be more interested in profit than revenue. But let's go with the kind of original idea that like we really are getting $3 extra back. Specifically, let's assume that the production cost, it should say here, the production cost is fixed. So if P denotes profit and the production cost is fixed, then what does r prime equals 3 imply about P prime? Okay, so this is a nice thing about derivatives. You only care about the next dollar. And since you've already paid all your production costs, the next dollar, if it generates $3 in revenue, is going to generate also $3 in profit. So even though calculating profit does require subtracting off all of those fixed costs, we don't have to think about those fixed costs because we're only worried about the small increase relative to the current value. So this is really the key idea about derivatives. It allows you to focus on what's happening sort of right here locally without taking into account things that are happening sort of in other regimes elsewhere on the graph. So, right, so the increase in revenue is 3 while the increase in cost is 0. So the total increase in profit is going to be 3. So again, this is a situation where drawing a graph, it's not clear what that really adds for you. You can think about, like, I spend an extra dollar, what happens? That gives you all the information you need to know to think about the derivatives of the functions involved here. So with that extra assumption that we have small or zero marginal production cost, or production cost on the next unit, then yeah, we're gonna basically get $2 free from spending an extra dollar on advertising. So totally, we're gonna do that. And we've already had some preview of this in some folks' answers, but we're looking at this situation where P prime is equal to 3. We put $1 on the table, we get $3 back. It looks like we're going to be sort of, pulling that arm as fast as we possibly can because it's just free money. Obviously, in the real world, that's not how things work, but sort of mathematically, what's going on here? What's going to stop this equation from telling us buy more, buy more, buy more forever? Okay, so people are totally on the ball with this one. So the problem is, of course, that the profit that you get from each increased dollar that you spend or each further dollar that you spend is going to go down. So the derivative being a certain value at a certain point doesn't tell you anything about what the derivative is going to be elsewhere. Derivatives can totally change. In general, they will. The only situation where derivatives don't change is if your function is completely flat. It's a graph is a straight line. And in the advertising situation, of course, what's going to happen is as you spend more money on advertising, you're going to saturate the market. You're going to reach everyone who's a really good fit for your product, and you're going to have to start making money from people who are slightly less of a good fit. And of course, in the limit towards infinity, you're going to run out of money. You're going to run out of people on the planet. I mean, effects set in long before that. But the point is that derivatives change in different regimes, and that's completely expected. I will take a step aside here because Yingfei pointed out that I made a mistake above. So the profit should be 2, not 3, because there's an extra dollar of ad spending that has to come out. So I was thinking of production cost here, but really, well, I don't know. I guess it's an accounting issue. Do you count the ad spending on the profit side? I guess you should. I'm definitely not an accounting specialist. So right. So in any case, it might seem like this whole discussion is sort of a distraction from the topic of calculus, or overly specific, maybe overly simple if you're used to thinking about these things. But I'm actually aiming here to give you another mental model for thinking about calculus ideas, because it's really clear in this ad spending context that we're talking about spending one more dollar and what's going to happen. It's all about the next dollar when we're talking about derivatives, and this is really where the value comes in of thinking about derivatives. This happens throughout applications of calculus when we talk about differential equations. This is something that really drives the sort of utility of this subject. It's often easier to reason locally about what's going to happen sort of right here with a small change right now than to think about what's going on everywhere all at once. That is brought into focus, I think, more with this particular example. And I'll give you a specific math idea that you develop in a calculus course that I think is simpler to think about in this context. So for example, the chain rule tells you that if you want to differentiate a composition, so you have a function g and another function f, and you want to consider the function that applies g and then applies f, and we want to differentiate that and basically understand how does the derivative of a composition relate to the derivatives of the functions themselves. And the chain rule says, here's your answer. You multiply the derivative of the outside function evaluated at the inside function's output value, and then multiply that by the derivative of the inside function. So basically what this is really saying is just that derivatives distribute across composition and they turn into products. But like this right-hand side looks kind of funky notationally. Like you've got G showing up twice here. It only shows up once. Like what's the deal with that? Like I really just want to maybe say like F prime of X times G prime of X. Wouldn't that be nicer looking than this stuff? And just, if you took calculus 1, you probably remember asking this question, or someone in your class asking this question, kind of having this confusion. And I think it's completely reasonable. You sort of want things to look more symmetric. But if we think about this formula in the context of the relationship between ad spending and revenue, it makes total sense. Like if, let's say X is the spending, that's the input. And let's say G is the revenue that the company will get from that spending. And let's say that you can compute the profit directly from the revenue. So there's some other function f, which says if you bring in this much revenue, you're gonna get a resulting profit. So that maybe that factors in production costs. So in this setting, it's really clear that you need to be thinking about the revenue change at the current spending level. So when you plug something into this function f, you really need to be thinking about that thing that you're plugging in as being revenue, because the function is built with that understanding. You're finding the function f to take in revenue values. And so if you try to plug in spending values directly into that function, it wouldn't make sense. It would give you nonsense results. So the structure of this formula in mathematical notation looks a little bit asymmetric and maybe not totally satisfying. But if you assign meaning to each of the components and think about what it means in that context, then it makes total sense. This is really the only way it could be. And it's very easy to think about like what each of the components means. So you spend an extra dollar and you get, a G prime dollar increase in revenue. But then maybe F prime is telling you have to temper that somewhat because of production costs. So that just scales down the profit. Like, so maybe you spend $1, you get $3 extra in revenue, but maybe you have 10% production cost. So in that case, F prime would be 90%. And that would just scale down your revenue a little bit. So like maybe one way to say what we're trying to say here is that mathematical quantities, so quantities that you deal with in a pure math context, like a Calculus 1 course, can be a little too homogeneous or sort of consistent in the way that they present. And so if you apply some real world interpretation where things have units, then it can make the ideas easier to think about because it gives you sort of mental hooks into the interpretation of what you're studying. Okay, so we have a few minutes left. I just want to get into this next part and we'll just pick up from there. I'm pretty close to the end of what I have prepared today. So I want to talk about another idea which sort of goes beyond what you study in a calculus course. So usually you'll see something like 1/1 plus e to the minus x, or some, combination of elementary functions and variables. That's kind of your bread and butter in a calculus course. But like, let's say you want to know how the S&P 500 is doing. You go to Google and you type in SPY. That's an exchange traded fund that tracks the S&P 500. So it's pretty much going to tell you what the S&P is doing. And Google is going to communicate a function to you, and it's not going to do that with an elementary function. What is it going to look like instead? All right, so folks are on the ball here. It's showing you a graph. Now, what I want to follow up there with, so yeah, it presents as a graph. Here's what the graph looks like. Everybody's seen this a million times probably, even just like walking around in airports when the financial news is on. What though is the data structure underlying this graph? So it's obviously not an elementary function. What is Google sort of handling behind the scenes? Google servers are doing some stuff here to render this graph for you. What kind of data do they manage in order to present this data to you or present this graph to you? Okay, so we have a few kind of ideas here, which is good. There is some variety in possible answers because we don't know exactly what Google is doing. But roughly speaking, here's what's going on. The graph is encoded in some way as a collection of time, price pairs. So we could store that as a list of tuples where each tuple has a time value in the first position and a price in the second position. Or we could store it in two lists where the understanding is that the indices align, so we'll have the same length, and any given, like the fifth entry of the time list will correspond to the fifth entry of the price list, something like that. We have more advanced data structures here that are being suggested. So a dictionary, so a key value store where keys are the times and values are the prices. Yep, that would work. Equivalently, you could have a 2-column matrix that uses one of the columns as an index to allow you to sort of quickly look up the values in the other column. That works. Yeah, this is sort of the root of what's going on. We have date time stamps and corresponding Y values. So I'll leave you with the next question I was going to ask so that we can pick up from here next time. We want to think about what it means to approximate derivatives in a context where a function is specified in this way. So I'll give you, I'll take the timer off, but I'll just give you the exercise for next time so you can think about it, and we'll pick up from here. So I'm giving you some NumPy code so you can make a plot and think about computationally what would you do with these two arrays to try to plot some sort of derivative approximation based on this list of x values and y values that go together.